Now let's talk about skew. Skew is when two sets of registers receive a clock that's slightly different. The edge is slightly different. The frequency is the same, but the edge does not coincide. So why does clock skew occur? Well, registers are placed at different locations across a chip, and so the delay of the clock wires or the clock lines may be slightly different, and the registers may even be on a different chip. So the clock is the same frequency, but the edges may be delayed from each other. So skew is the difference between the two clock edges. And we're always going to perform a worst case analysis to guarantee that we don't violate dynamic discipline for any register. There are many registers in the system, and we'll perform this analysis for the worst case of a pair of registers. And we always do timing analysis between pairs of registers. So here's an example. So we have clock 2, and there's some big delay in clock 1. So clock 1 is delayed from clock 2, and that difference is the skew. We put these hash lines because it could be, depending on different parameters, could be slightly less or slightly more, but this is the maximum delay between the clock edges, and that's called the skew. So now let's consider both of our timing constraint questions, setup time constraint and hold time constraint, in terms of skew. So in terms of the setup time constraint, the worst case is when clock 2 is earlier than clock 1. So when clock 2 here is earlier than clock 1. So we can see that clock 1 is here, but clock 2 is skewed earlier. And so we get a clock edge, clock 1 here. We get this clock edge. But now clock 2 is early by some amount, by t skew. And so instead of having this entire cycle time to do that work, propagation clock to Q, propagation delay and setup, we actually only have TC minus t skew. This clock edge is t skew earlier. And so instead of having that whole TC to do our work, which is get out of the flip-flop, go through the combinational logic, and set up at the far register, at the rightmost register, now instead of having the entire TC, we just have TC minus T skew to do that work. Because clock 2 is skewed earlier from clock 1 by T skew. And so written nicely, we have, instead of our entire cycle time, we only have TC minus T skew, or we can put T skew plus T skew for both sides. Bring T skew over to the right side, and we get the equation shown here. And again, we could write this in terms of our TPD as well, and we get this equation. But you can always derive that from thinking about it and writing the original equation. And so we actually have to make our, if we notice from this equation here, we have to increase our cycle time by t skew, our minimum cycle time by t skew, to account for t skew. So now our circuit is running at a slower frequency than it had been without skew. Now let's, for a moment, think about, well, why didn't we say the worst case was clock 2 being later than clock 1? So let's see what happens in that case. This is not the worst case. This is why we don't consider it. But here's clock 1, and here's clock 2, where clock 2 is later than clock 1. Again, same frequency. So T skew, but now it's skewed later. This is still our T skew. Well, what happens now? So here's our cycle time still. Clock 1 clocks in our our data, right? We get a clock edge, and clocks in the data, clock 1. But now clock 2 here in blue, clock 2 is what's clocking out our data into register 2. So now instead of cycle time, just the cycle time, we actually have TC plus T skew. This is not the worst case. TC plus T skew is greater than or equal to, well, all that same work, TPCQ plus TPD plus T setup. The same stuff we had, right? This stuff. But now, right, we actually get more time if clock 2 is later than clock 1. So it's definitely not the worst case. So in that case, we would have TC is greater than or equal to all that stuff that we have to do, propagation clock to Q, test plus TPD plus T setup. But now we could bring the skew over to the other side, subtract it from both sides, and get minus T skew. So actually in that case, we could run it at a smaller cycle time or a faster frequency. Okay, so that is not the worst case. This is the worst case. We always want to do the worst case because, well, we don't know which way it's skewed, but we're going to assume the worst case so that no matter which way it's skewed, it will work. No matter which way the clocks are skewed. So now let's consider the hold time constraint. So now let's consider the hold time constraint with skew. So in the worst case, clock 2 is later than clock 1. So clock 2 here is, again, the clock going into R2. With the hold time constraint, we're worried about this near edge, the same clock edge. And so clock 2 still has this hold time constraint, T hold, let's call it TH. But now it's gotten worse, right? When they were coincident, clock 1 and clock 2 were the same. Clock 1, clock 2, it had some hold time constraint here, T hold. We had to make sure that clock 1 was driving clock 1's driving our data out. We had to make sure that a fast path, TCCQ, plus T contamination delay, right, the path to get here to here, that fast path was not so fast that it was shorter than T hold. Right? So it would start changing D2 here. And so now we've made it worse because we're actually saying, okay, this is clock 2. We're actually now saying, well, not only is it, this one doesn't violate it, right? T hold is less than TCCQ plus TCD, so no problem on that one. But what happens when we move this later? Now we're going to move clock 2 so that it's, instead of being there, it's now skewed later. It still has its hold time constraint, TH. But now TCCQ plus TCD has to be greater than, right, the amount that is skewed, T skew, that's the amount that is skewed, plus T hold instead of just T hold. Right, in this case, you can see this violates that hold time constraint. It starts changing before that hold time constraint is met, right? This D2, if we were to draw D2, could start changing as early as TCCQ plus TCD past clock 1's edge. You can see that that is changing within clock 2's hold time when clock 2 is skewed by some amount T skew. And so again, we can write this equation, T hold plus T skew has to be less than TCD plus TCCQ. Or in other words, this has to be greater than our hold, not just our hold now, but our hold plus the amount that it was skewed. Skew. And we can write this in terms of what we have control over, our contamination delay, and just bring TCCQ onto the other side. And so we've made this one harder too, right? This is already a fast path. Now it has to be larger than, greater than a larger number. Right? It used to just be greater than T hold, but now we've made it even harder. That fast path, that small amount, has to be now greater than T hold plus T skew. And we can do the thought experiment about why this is the constraint again. So here's clock 1 and clock 2. Clock 1. If clock 2 were skewed early, instead, right, clock 2 is later than clock 1. But if instead it had been early, so here's clock 1, clock 1. And if clock 2 had been skewed early, right, here's T skew. Well, now it's hold time constraint. Maybe it was there or something relative to its clock edge. Now we just made it better, right? This is a short amount of time that this TCCQ plus TCD has to be greater than.